You are sitting somewhere right now, probably in a chair, in a room, on solid ground. You can feel the weight of your body pressing down. You can trust that floor beneath you. You trust that time is moving forward, 1 second after the next, like it always has. But what if I told you that in 2023, scientists proved that time has holes in it, that they can punch slits into the fabric of time itself, the same way you might cut holes in a piece of paper? What if I told you that the heaviest particles in the known universe, particles that exist for less than a trillionth of a second, are communicating with each other instantly, across distances that should make such communication impossible? What if I told you that scientists have built an engine that runs on nothing, not heat, not fuel, nothing but the pure mathematics of existence itself? What if I told you that energy can be teleported from empty space, from the vacuum itself, extracted from what should be absolute nothingness? And what if I told you that the force pushing the universe apart, the mysterious dark energy that will determine the fate of everything that exists, might be fading away right now as we speak, and that the long-term forecast for reality itself is being rewritten? These are not thought experiments. These are not philosophical musings. These are not fringe theories from scientists chasing headlines. These are peer-reviewed discoveries, published in Nature and Physical Review, confirmed by the largest physics laboratories on Earth, reproduced by independent teams across multiple continents, and almost nobody talked about them. The news cycle moved on. The algorithm showed you something else. These discoveries, any one of which would have dominated scientific discourse for decades in an earlier era, slipped through the cracks of our attention economy, like water through sand. The question is not just why. The question is what we are missing by not paying attention. What does it mean for our understanding of reality when the most fundamental aspects of existence, time, space, matter, energy, and the fate of the cosmos, are being revealed in ways that challenge everything we thought we knew, and we simply do not notice? I'm going to tell you about 5 discoveries. 5 moments when the veil between what we understand and what is actually true was pulled back just a little. By the end, you may not see the world the same way. Let us begin. Let us start with something you think you understand. The double-slit experiment. If you have ever taken a physics class, you have probably heard of it. Thomas Young first performed this experiment in 1801, and it fundamentally changed our understanding of light. The setup is beautifully simple. You take a barrier with 2 narrow slits in it. You shine light through those slits, and you observe what pattern appears on a screen behind the barrier. If light were made of particles, like tiny bullets, you would expect to see 2 bright lines on the screen, one behind each slit. But that is not what happens. Instead, you see an interference pattern. Bands of light and dark rippling outward like waves colliding on the surface of a pond. This proved that light behaves as a wave. But here is where it gets strange. In the 20th century, physicists discovered that if you send photons through the slits one at a time, they still create an interference pattern. A single photon, an indivisible particle of light, somehow interferes with itself, as if it travels through both slits simultaneously, as if it exists in 2 places at once, and only decides where it actually is when you look at it. This is not a metaphor. This is not a simplification for popular audiences. This is what the experiments show, over and over again. The photon does not secretly go through one slit or the other. It genuinely, in some quantum sense, goes through both, until you set up a detector to watch which slit it goes through. And then, mysteriously, the interference pattern disappears. The act of observation changes the outcome. The universe seems to care whether you are watching. Richard Feynman, perhaps the greatest physicist of the 20th century, once said that all of quantum mechanics can be gleaned from carefully thinking through the implications of this single experiment. He called it the heart of quantum mechanics. He also said that nobody understands quantum mechanics, and he included himself in that assessment. For over 2 centuries, the double-slit experiment has been the cornerstone of our understanding of wave-particle duality. It has been performed with photons, with electrons, with neutrons, even with entire molecules containing dozens or hundreds of atoms. Buckyballs, football-shaped carbon molecules made of 60 atoms, have been sent through double slits and have produced interference patterns. Every time, the same strange result. The quantum world refuses to behave like the world we think we know. It refuses to give straight answers to straight questions. It insists on ambiguity, on superposition, on the fundamental importance of the observer. But in April 2023, a team of physicists at Imperial College London did something unprecedented. They performed the double-slit experiment in time. Stop and think about what that means. Really sit with it for a moment. The original experiment creates slits in space. 2 physical openings, separated by a distance you can measure with a ruler. Simple, tangible, real in the way that everyday objects are real. But time is different. Or at least, that is what we have always believed. Space is something you can move through, forwards and backwards, left and right. You have control. But time moves you. Time is the river that carries everything. You cannot step outside of it. You cannot cut holes in it. Time is not a thing. It is the background against which all things happen. At least, that is what we thought. That is what generations of philosophers and physicists assumed. Even Einstein, who showed that time and space are woven together in a single fabric called space-time, even Einstein treated time as something that could be stretched or compressed by gravity and velocity, but not punctured, not given holes the way a piece of paper can be given holes. The Imperial College team proved that assumption wrong. The original experiment creates slits in space, 2 openings separated by a physical distance. But time is supposed to be fundamentally different from space. Time flows. Time is the backdrop against which all events unfold. You cannot cut holes in time the same way you cut holes in a piece of cardboard. Except, it turns out, you can. Professor Riccardo Sapienza and his team achieved this by using a material that can change its optical properties in femtoseconds. A femtosecond is 1/4 of a second. If the entire history of the universe, from the Big Bang to this exact moment, were compressed into a single second, a femtosecond would be equivalent to a single day. The team used a thin film of indium tin oxide, the same material that forms most mobile phone screens. Normally transparent, this material can be switched to become reflective when hit with a pulse of laser light. The switch happens so fast that it creates what the researchers call a temporal slit, a moment in time where light can pass through, followed by a moment where it cannot, followed by another moment where it can again. 2 temporal slits, not holes in space, holes in time. And here is the result that should have been on every news channel, in every science publication, discussed in every classroom. When light passes through these time slits, it creates an interference pattern, just like the spatial version. But instead of bands of light and dark appearing in different locations, the interference shows up as changes in the frequency of the light. Different colors emerge, colors that interfere with each other, enhancing and cancelling out, creating patterns that should not exist. Professor Sir John Pendry, who worked on the experiment, described its significance in measured but profound terms. He said the double time slits experiment opens the door to a whole new spectroscopy, capable of resolving the temporal structure of a light pulse on the scale of one period of the radiation. That sounds technical. That sounds like something only specialists would care about. But let me translate what this actually means. Let me show you why this should have been front-page news. Space and time, at the quantum level, are not as different as we thought. The fundamental weirdness of quantum mechanics, the interference, the superposition, the refusal of reality to be pinned down until you look at it, these properties extend into time itself. Time is not just a river flowing in one direction. Time is not just a parameter that ticks forward on your watch. Time is a medium that can be manipulated, structured, shaped, punctured, and reformed. Romain Tirole, the lead researcher on the experiment, put it even more dramatically. He and his colleagues wrote that showing diffraction from a double slit in time requires flicking a switch extremely fast, on timescales comparable to how fast the light field oscillates, about a few femtoseconds. And then he offered this comparison. If the entire history of the universe from the Big Bang to the moment you read this was a second, an oscillation of light would only take the equivalent of a single day. That is how fast their temporal slits are. That is how precisely they can now manipulate the structure of time. The implications reach far beyond academic curiosity. The researchers suggest this could lead to time-varying metamaterials, materials with properties we have never seen before, materials that can control light in ways that should be impossible. They mention, almost casually, that their work promises enhanced wave functionalities such as non-reciprocity, new forms of gain, time reversal, and optical Floquet topology. Time reversal, listed there in the middle of a scientific sentence. Not a speculation, not a science fiction, as a genuine physical possibility enabled by this research. They also want to explore what they call time crystals, structures where optical properties vary periodically in time rather than in space. Professor Stefan Meyer, a co-author on the study, said that the concept of time crystals has the potential to lead to ultra-fast, parallelized optical switches. The findings were published in Nature Physics. They represent one of the most profound demonstrations of the equivalence between space and time at the quantum level. They open doors to technologies and possibilities that seemed like fantasy just a few years ago. And yet, most people have never heard of them. The experiment that fundamentally challenged our understanding of time, that showed we can punch holes in the temporal fabric of reality, that brought time reversal from the realm of fantasy into the realm of near-term engineering goals. This experiment passed through the news cycle like a ghost, here and then gone, barely noticed. This is not how science news should work. This is not how we should treat discoveries that reshape our understanding of existence. But this is just the beginning. Now I want to take you somewhere much larger, to the largest particle accelerator ever built, the Large Hadron Collider at CERN, straddling the border between Switzerland and France, 27 kilometers in circumference, buried 100 meters underground. Inside this machine, protons are accelerated to 99.99991% of the speed of light. They collide with such violence that for a brief instant, conditions exist that have not occurred naturally since a trillionth of a second after the Big Bang. In these collisions, the fundamental building blocks of matter reveal themselves. One of these building blocks is the top quark. It is the heaviest elementary particle known to science. A single top quark weighs about as much as an entire gold atom, which is extraordinary for something that has no internal structure, no components, no parts. It is, as far as we know, truly fundamental. Top quarks are also incredibly unstable. They exist for about 0.5 yoctoseconds. That number, written out, is 0.05 seconds. In that unimaginably brief window, the top quark decays into other particles before it has time to interact with anything through the strong nuclear force. This brevity would seem to make top quarks useless for studying quantum entanglement. Entanglement requires particles to remain connected, to share information instantaneously across distance. How can something that exists for half a yoctosecond become entangled with anything? But in September 2023, the Atlas collaboration at CERN announced the first ever observation of quantum entanglement between top quarks, and later the CMS collaboration confirmed it independently at the highest energies ever recorded in particles that exist for almost no time at all. Let me explain what they found and why it matters so much more than the brief news coverage suggested. When proton beams collide at the LHC, they sometimes produce a pair of particles, a top quark and its antimatter counterpart, an anti-top quark. These particles fly apart and almost immediately decay. The top quark does not have time to interact with anything. It does not have time to form composite particles like the protons and neutrons that make up your body. It simply winks into existence and then is gone. But despite their separation, despite their infinitesimal lifespans, despite existing for less time than light would need to cross the width of a proton, the spins of these particles remain correlated, entangled. To understand what this means, you need to understand spin. Spin is a quantum property of particles. It is not exactly like a spinning top or a rotating planet. It is something more abstract, a fundamental quantum number that describes how particles behave under rotation. For our purposes, the important thing is that a particle's spin can be measured, and that measurement has a random outcome, either spin up or spin down along whatever axis you choose. If two particles are entangled, their spin measurements are correlated. If you measure one particle and find spin up, and your colleague measures the other particle along the same axis, they will find spin down. Every time, without fail, even if the particles are light years apart, even if there is no way any signal could have passed between the measurement events. This correlation is what Einstein called spooky action at a distance. He did not believe it could be real. The Atlas and CMS collaborations measured this correlation by looking at the decay products of the top quarks. Specifically, they measured the angles at which charged leptons emerged from the decays. If the top quark and anti-top quark were entangled, the statistical pattern of these angles would show specific correlations predicted by quantum mechanics. And they did, with a significance exceeding 5 standard deviations, the threshold that physicists use to declare a discovery. 5 sigma means there is less than a 1 in 3.5 million chance that the result is a statistical accident. This is not suggestive. This is not preliminary. This is definitive. Andreas Höcke, the Atlas spokesperson, called the observation remarkable. He said it paves the way for new investigations into this fascinating phenomenon. But what does it actually mean? The CMS collaboration went further in their analysis. They examined cases where the 2 top quarks were produced moving at high speed relative to each other. In these scenarios, the particles decayed so far apart in space and at times so separated that any classical exchange of information between them was impossible. The decays occurred beyond what physicists call the light cone, the boundary of causality. No signal traveling at or below the speed of light could have connected the 2 events. And yet, the spins remained correlated, still entangled. Einstein called quantum entanglement spooky action at a distance. He did not believe it was real. He thought it was a sign that quantum mechanics was incomplete, that there must be hidden variables, local information carried by the particles themselves that explained the correlations without invoking anything mysterious. In 1964, physicist John Bell proved mathematically that any hidden variable theory would produce statistical predictions that differ from quantum mechanics. And in decades of experiments since, quantum mechanics has won every test. The correlations are real, the spookiness is real. But all previous tests of entanglement had been conducted at relatively low energies, with photons, with atoms, with particles that exist long enough to be carefully prepared and measured. No one had confirmed that entanglement works the same way at the energy scales probed by the LHC, at the frontiers of physics, in the regime where gravity and quantum mechanics might finally reveal how they fit together. Now we know. Entanglement persists at the highest energies ever tested. The heaviest elementary particles, existing for the briefest instance imaginable, still exhibit this fundamental quantum correlation. Patricia McBride, the CMS spokesperson, said that with measurements of entanglement and other quantum concepts in a new particle system and at an energy range beyond what was previously accessible, we can test the standard model of particle physics in new ways and look for signs of new physics that may lie beyond it. Look for signs of new physics that may lie beyond it. This is not a throwaway phrase. This is not scientific hedging or empty speculation. This is the stated motivation for the most ambitious physics experiments on Earth. This is not a small statement. The standard model, our best description of particle physics, has reigned supreme for half a century. It predicted the existence of the W and Z bosons before they were discovered. It predicted the existence of the top quark itself before it was found in 1995 at the Tevatron. It predicted the existence of the Higgs boson before it was discovered at the LHC in 2012. Every time experimentalists have built a machine capable of testing the standard model at new energy scales, the theory has passed with flying colors. But physicists know it must be incomplete. It does not include gravity. It cannot explain why neutrinos have mass. It does not tell us what dark matter is. It cannot tell us why the universe exists at all. Entanglement at these extreme scales is one such probe. If quantum mechanics worked differently at high energies, If entanglement weakened or disappeared, that would be revolutionary. It would point toward new physics. The fact that entanglement persists, that top quarks and anti-top quarks stay correlated despite everything, is itself a profound result. It closes off certain possibilities. It constrains what the deeper theory could be. And the story of quantum behavior at extreme scales does not end there. In May 2023, researchers at Quantinuum, using their H2 trapped ion quantum computer, announced the first creation and manipulation of non-abelian anyons. These are exotic quasi-particles that had been predicted for decades but never observed. Unlike ordinary particles, which either bunch together like bosons or exclude each other like fermions, non-abelian anyons have even stranger statistics when you braid them around each other, swapping their positions in specific ways. The quantum state of the system changes in a manner that depends on the order of the swaps. This is profound because it suggests a new way to build quantum computers. The information in a non-abelian system is stored topologically, in the patterns of how particles have been moved around each other. This makes the information resistant to certain kinds of errors. The qubit is protected not by clever engineering, but by the fundamental mathematics of topology. Elias Khan, Chief Product Officer at Quantinuum, called it potentially a transistor moment for the quantum computing industry. The creation and manipulation of non-abelian anyons to create topological qubits is another example of using quantum systems to explore and create other quantum systems. This is precisely what Feynman anticipated when he proposed the idea of quantum computation. And yet this too passed with far less attention than it deserved. The door to using entanglement and other quantum phenomena to test the standard model in ways that have never been possible before is wide open. A door that almost nobody told you about. Now let us go somewhere stranger still. Into the quantum vacuum. Into the emptiness between the stars. Into the nothing that turns out to be everything. Most people think of a vacuum as emptiness, the absence of matter, the void. If you could pump all the air out of a chamber, you would have a vacuum. If you could remove every particle, every atom, every bit of dust, you would have perfect emptiness. Nothing. But quantum mechanics tells a completely different story. And this story is one of the strangest in all of physics. The vacuum is not empty. It seethes with activity. It writhes with invisible energy. Even in the coldest, darkest, most isolated corner of the universe, things are happening. Particles and their antiparticles constantly pop into existence out of pure nothingness, borrowing energy from the universe for the briefest instants before annihilating and returning what they borrowed. These are called virtual particles. They appear and disappear so quickly that you cannot measure them directly, but their effects are measurable. Their shadows fall on experiments. These are called vacuum fluctuations. They are not hypothetical. They are not mathematical abstractions that physicists use to make their equations work. They have real, measurable effects that have been confirmed in laboratories around the world. The Casimir effect, for example. Place two uncharged metal plates very close together, a few nanometers apart, and they will attract each other. Why? Because the vacuum fluctuations outside the plates have more modes, more ways to exist, than the constrained fluctuations between the plates. The imbalance creates a pressure, a measurable, demonstrable force arising from the quantum nature of empty space. This effect was predicted by Hendrik Casimir in 1948 and has been measured to extraordinary precision. The Lamb shift is another example. The energy levels of the hydrogen atom are slightly different from what you would calculate using basic quantum mechanics, because the electron interacts with the vacuum fluctuations around it. Willis Lamb measured this shift in 1947, and it led to the development of quantum electrodynamics, one of the most accurate scientific theories ever created. The anomalous magnetic moment of the electron provides perhaps the most striking example. The electron's magnetic properties, when calculated, including vacuum fluctuation effects, agree with experimental measurements to 11 decimal places. That is, a precision of 1 part in 100 billion. This agreement between theory and experiment is one of the crown jewels of physics. So the vacuum is not empty, it seethes with activity. But here is what makes the vacuum truly strange, truly counterintuitive, truly worthy of your attention. Even in its lowest energy state, the ground state, the vacuum contains energy, 0-point energy. And according to the most straightforward interpretation of quantum mechanics, you cannot extract it. You cannot reduce the vacuum's energy below its minimum. The vacuum is already at the floor. There is no basement to descend into. Or so we thought. In 2008, Japanese physicist Masahiro Hotta, working at Tohoku University, proposed something that seemed to violate this principle. He called it quantum energy teleportation. The name sounds like science fiction. It sounds like something from a Star Trek episode, not a physics paper. But the mathematics was rigorous. The peer review was thorough. Hotta showed that if you have two parties, traditionally called Alice and Bob in physics thought experiments, who share an entangled state, you can perform a kind of magic trick. Alice makes a measurement on her part of the vacuum. This measurement injects energy into the system. She then sends the result of her measurement to Bob through a normal classical channel, like a phone call or an email. Bob uses that information to perform a specific operation on his part of the vacuum. And when he does, he can extract energy from his local region of the vacuum. Not create energy, extract it. The energy Bob extracts is less than or equal to the energy Alice injected. The books still balance, but the energy appears at Bob's location before Alice's injected energy could possibly have traveled there through normal means. For 15 years, this remained a theoretical curiosity. The protocol was proven mathematically sound, but no one could implement it experimentally. The precision required was beyond available technology. The energy differences were too tiny to measure. Then in 2023, everything changed. Two separate teams demonstrated quantum energy teleportation experimentally. First, in March 2023, researchers at the Institute for Quantum Computing at the University of Waterloo, led by Raymond Laflamme and Eduardo Martín Martínez, published their results in Physical Review Letters. They used nuclear magnetic resonance to simulate the quantum system of a vacuum using 3 carbon atoms in the molecule transcrotonic acid. Their experiment showed that extracting energy from an entangled ground state is possible. As Laflamme put it, it is a small step, but it opens the door for many other things. Quantum information science is becoming quantum information technologies, but the more dramatic demonstration came from Kazuki Ikeda, a physicist at Stony Brook University. He used IBM's superconducting quantum computers to demonstrate quantum energy teleportation in a system that operates near absolute zero, in the millikelvin regime where quantum effects dominate. The results were published in Physical Review Applied in August 2023. Let me describe what Ikeda actually did in more detail. Ikeda used several of IBM's publicly accessible quantum computers, including IBM Q Jakarta, IBM Q Cha Lima, and IBM Cairo. These machines operate at temperatures around 15 millikelvin, colder than outer space, using superconducting circuits as qubits. He implemented the basic quantum energy teleportation protocol between two qubits, carefully designed to match the theoretical predictions. The key result was the observation of negative expectation values of extracted energy. Let me unpack what that means in plain language. Bob's region of the quantum computer ended up with less energy than the vacuum state should allow. The expected energy at Bob's location, after all the operations were performed, was below the ground state energy. Energy had been teleported from Alice's region to Bob's region. Without quantum error correction, the results were noisy. In some runs, Bob's extracted energy appeared positive, indicating the protocol had not worked. But when Ikeda applied sophisticated error correction techniques, the values shifted. They became negative. The teleportation succeeded. The amounts were tiny, almost immeasurably small. Bob received roughly 1 to 5% of the energy Alice injected. But the principle was clear. The classical communication between Alice and Bob took about 10 nanoseconds, which was much faster than the energy could have propagated through the system by normal physical means. Ikeda wrote that his results provide a realistic benchmark that is fully achievable with current quantum computing and communication technologies. This is not a projection for the future. This is a statement about what we can do right now. Even more remarkably, Ikeda is working on extending the protocol to longer distances. He has proposed a setup for long-distance and large-scale quantum energy teleportation, using the quantum network between Stony Brook University and Brookhaven National Laboratory, a distance of approximately 150 kilometers. Energy teleported across Long Island, not in a science fiction movie, in a research proposal based on demonstrated technology. Think about what this means. We have developed a protocol for moving energy from one location to another without any physical carrier in between. Not through wires, not through radiation, not through particles traveling through space, through the manipulation of quantum correlations. This is not science fiction. This is peer-reviewed physics, published in Physical Review Applied. The code is publicly available on GitHub. Anyone with access to IBM's quantum computers can, in principle, replicate the experiment. The practical applications are still far off, of course. The energy amounts are minuscule. We are talking about fractions of the energy carried by a single photon. The equipment is expensive and finicky, requiring temperatures near absolute zero and precise control of quantum states. Nobody is going to be powering their home with teleported energy anytime soon. But that is not the point. The point is that a theoretical prediction from 2008, a wild idea about extracting energy from the quantum vacuum using entanglement, has been demonstrated experimentally. The universe works the way Masahiro Hotta said it would. The vacuum is accessible in ways we did not think possible. And there are deeper implications. Hotta and others have shown connections between quantum energy teleportation and some of the deepest problems in physics. The protocol relates to the black hole information paradox, the puzzle of what happens to information that falls into a black hole. It connects to questions about quantum thermodynamics, and the fundamental limits on energy extraction. It may even provide insights into the nature of quantum gravity itself. Kazuki Ikeda has explored these connections. He showed that quantum energy teleportation can be used to probe phase transitions in quantum field theory, transitions between different states of matter that may have occurred in the early universe. He showed that the amount of energy that can be teleported is related to quantum correlations called discord, providing a new way to measure and characterize quantum information. This is foundational physics. This is the kind of work that, in earlier decades, would have been the subject of breathless news coverage and popular science books, and almost nobody noticed. The fourth discovery I want to tell you about reaches into the heart of what it means for matter to exist. All particles in nature fall into one of two categories: bosons or fermions. This is not a classification scheme invented by physicists. It is a fundamental feature of reality, built into the mathematics of quantum mechanics. Bosons are gregarious. They like to be together. Photons are bosons, which is why lasers work. Photons can pile into the same quantum state, all doing exactly the same thing, reinforcing each other. Fermions are loners. The Pauli exclusion principle forbids any two identical fermions from occupying the same quantum state. Electrons are fermions. This is why atoms have the structure they do, why chemistry works, why you do not fall through your chair. The electrons in your atoms cannot all collapse into the same state. They are forced to spread out, to occupy different energy levels, to create the complex structures that make matter solid. At everyday temperatures, the difference between bosons and fermions is subtle. Particles are moving around, colliding, occupying many different states. But at extremely cold temperatures, near absolute zero, the difference becomes profound. Cool a collection of bosons to near absolute zero, and they all collapse into the lowest energy state, a Bose-Einstein condensate, a blob of matter behaving as a single quantum entity. Cool a collection of fermions to near absolute zero, and something very different happens. They cannot all collapse to the same state, so they stack up, each fermion occupying a successively higher energy level. The energy of the whole system is vastly higher than if they were bosons. This energy difference is enormous. Let me give you a sense of scale. For a one-dimensional harmonic trap containing n fermions versus n bosons, the energy difference scales with n squared. That means if you double the number of particles, the energy difference quadruples. For large numbers of particles, this Pauli energy becomes immense. It is the reason neutron stars do not collapse into black holes. The degeneracy pressure from fermions, the sheer energetic resistance to being pushed into the same quantum state, can balance the gravitational crush of a star, twice the mass of our sun. And for decades, physicists have wondered, can you harness it? Can you build a machine that runs on this quantum pressure? Can you extract work from the simple fact that fermions and bosons obey different rules? In September 2023, a collaboration between researchers at the Okinawa Institute of Science and Technology, the University of Kaiserslautern Landau, and the University of Stuttgart did exactly that. They built a working engine powered by the quantum nature of matter itself, not by heat, not by fuel, by the simple fact that fermions and bosons have different amounts of energy. The paper was published in Nature. The lead authors included Jennifer Koch, Kirthi Menon, and Arthur Widerer. Here is how it works. The key insight is that you can change the quantum statistics of particles using magnetic fields. The team started with a cloud of lithium-6 atoms, cooled to temperatures just above absolute zero, using a combination of laser cooling and evaporative cooling. At these temperatures, approximately 10 nanokelvin, the thermal energy of the particles is so low that quantum effects dominate their behavior completely. The particles no longer move like classical balls bouncing around. They become waves smeared out over space, described by quantum mechanical wave functions. At these temperatures, pairs of fermionic lithium atoms can bond together to form diatomic molecules. And here is the crucial point. Each molecule, made of two fermions, is itself a boson. Two fermions, each with spin 1/2, combine to make a particle with integer spin. And particles with integer spin are bosons. They obey Bose-Einstein statistics, not Fermi-Dirac statistics. They compile into the same quantum state. By tuning a magnetic field, the researchers could control whether the atoms existed as individual fermions or as paired-up bosonic molecules. This is called a Feshbach resonance. It is a technique that has been used in cold atom physics for years, but no one had used it to build an engine. The engine works in 4 strokes, like a car engine. First, the bosonic molecules are compressed in an optical trap. The compression requires some energy input, but because bosons all occupy the same low energy state, the energy cost is relatively small. Second, the magnetic field is changed to break up the molecules. The bosonic molecules dissociate into individual fermionic atoms. But now there is a problem. All those fermions cannot occupy the same state. They are forced to spread out across many energy levels. The total energy of the system suddenly increases dramatically. Third, the trap is expanded. The high-energy fermionic gas pushes outward, doing work on its environment. This is where the engine delivers its output. Fourth, the magnetic field is changed back, allowing the fermions to recombine into bosonic molecules. The cycle resets. The engine achieved an efficiency of up to 25%. This is remarkable. The researchers believe that with further optimization, efficiencies above 50% are possible. Professor Thomas Bush, one of the leaders of the research, explained the fundamental principle. He said that to turn fermions into bosons, you can take 2 fermions and combine them into a molecule. This new molecule is a boson. Breaking it up allows you to retrieve the fermions again. By doing this cyclically, we can power the engine without using heat. This is an engine that runs on the difference between being a boson and being a fermion. It runs on the mathematics of identity, on the Pauli exclusion principle, on the fundamental rules that dictate how matter can exist. When Arthur Widera was a student, learning about the Pauli exclusion principle for the first time, he wondered whether the enormous energies associated with it could ever be used. At the time, the answer was no. There was no way to switch particles between bosonic and fermionic behavior. But the development of Feshbach resonance techniques changed that. And now, decades later, the dream has become reality. The engine is tiny. It operates at temperatures near absolute zero. It will not power your car or your phone, but it is a proof of concept for something we have never seen before, a thermodynamic cycle that does not use heat as its energy source. And this discovery connects to another remarkable finding from 2023 that deserves mention. In August of that year, Professor Chung Chin at the University of Chicago announced the first observation of quantum superchemistry. This is a related phenomenon where particles in the same quantum state undergo chemical reactions collectively all at once, rather than one collision at a time. In classical chemistry, reactions happen through random collisions. Atoms and molecules bounce around, and when they happen to hit each other with the right energy and orientation, they may form bonds or break apart. The process is fundamentally statistical. You cannot predict which specific atoms will react. You can only calculate probabilities and rates. But Chin's team showed that in a Bose-Einstein condensate, where all the atoms occupy the same quantum state, chemistry works differently. The atoms react together as a collective, thousands of cesium atoms bonded simultaneously to form cesium molecules, then near instantaneously converted back to cesium atoms. The oscillations were visible. The collective behavior was unmistakable. As Chin explained, you are no longer treating a chemical reaction as a collision between independent particles, but as a collective process. This has been a scientific goal for 20 years. It opens the possibility of controlling chemical reactions with unprecedented precision, steering molecules into specific states that would be random in classical chemistry. The links between classical and quantum physics have never been clearer, and yet the news barely made a ripple. The final discovery I want to share with you is perhaps the most unsettling of all, because it does not concern the small or the strange. It concerns the largest scales imaginable, the fate of the entire universe, the question of how everything ends. Since 1998, we have known that the universe is accelerating. Galaxies are moving apart from each other faster and faster. This was one of the most shocking discoveries in the history of cosmology. For decades, astronomers had assumed the opposite. They thought gravity would be slowing the expansion down. The Big Bang flung matter outward, and gravity should have been pulling it back, like a ball thrown into the air that eventually falls. Two teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the other led by Brian Schmidt at the Australian National University with Adam Rees at Johns Hopkins, set out to measure this deceleration. They used type I supernovae as standard candles, explosions so predictably bright that their distance can be calculated from their apparent brightness. By measuring how fast these distant supernovae were receding and how far away they were, the teams expected to calculate the rate at which the universe's expansion was slowing. They found the opposite. The universe is not slowing down. It is speeding up. Something is pushing the galaxies apart. Something is overcoming gravity. Something is making the expansion accelerate. We call that something dark energy, which is really just a placeholder name for our ignorance. We do not know what dark energy is. We do not know where it comes from. We do not know why it exists. We only know that it exists because we can see its effects, and those effects are enormous. Dark energy makes up roughly 68% of the total energy content of the universe. It is the dominant component of existence. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for their discovery. It was that important. For the past 2 decades, the standard model of cosmology has included a cosmological constant. This is the simplest form of dark energy, a fixed amount of energy inherent to empty space itself. Every cubic meter of vacuum contains the same tiny amount of energy, And as space expands, more vacuum is created, so more dark energy appears. The effect is cumulative. The more space expands, the more dark energy there is to push it to expand further. Einstein first proposed the cosmological constant in 1917 and later called it his biggest blunder. He had introduced it to keep his equations stable, to prevent the universe from collapsing under its own gravity. When Edwin Hubble discovered that the universe was actually expanding, Einstein regretted adding the constant. It seemed unnecessary. But when we discovered the accelerating expansion, the cosmological constant was resurrected. It fit the data beautifully. It was simple. It was elegant. Licia Verde, a cosmologist, explained the appeal to Quanta magazine. She said it is simple. It is one number, and physicists often use aesthetics as a guide in seeking explanations. Simplicity and elegance matter. But in 2024, something changed. The simple, elegant explanation began to crack. The Dark Energy Spectroscopic Instrument, or DESI, began releasing results from its survey of the cosmos. DESI is an extraordinary machine. Mounted on the Nicholas U. Mayol 4-meter telescope at Kitt Peak National Observatory in Arizona, it can capture light from 5,000 galaxies simultaneously. 5,000 tiny robotic arms position fiber optic cables to capture light from individual galaxies. Every 20 minutes, the robots reconfigure and capture light from 5,000 more objects. By measuring the redshifts of millions of galaxies and quasars, DESI can map the three-dimensional structure of the universe across billions of years of cosmic history. The technique DESI uses is based on something called baryon acoustic oscillations. In the early universe, before the first atoms formed, matter and radiation were locked together in a dense plasma. Sound waves rippled through this plasma, creating regions of slightly higher and lower density. When the universe cooled enough for atoms to form, the pattern of these sound waves was frozen into the distribution of matter. This pattern, like a cosmic ruler, can be measured at different distances and times, allowing cosmologists to track how the universe has expanded. In April 2024, the DESI collaboration announced their first-year results at a meeting of the American Physical Society. The data suggested something unexpected. Dark energy might not be constant. It might be changing over time, and specifically, it might be weakening. The initial hints were tantalizing, but not conclusive. The statistical significance was around 3 sigma, meaning there was roughly a 1 in 300 chance the result could be a statistical fluke. Interesting, but not enough for a discovery claim in physics, which typically requires 5 sigma significance. The collaboration urged caution. Adam Rees, one of the original discoverers of dark energy, told New Scientist that if the result holds up, this is a very big deal. It may be the first real clue we have gotten about the nature of dark energy. Then in March 2025, they released their 3-year results. With nearly 15 million galaxies and quasars measured, more than double the previous dataset, the precision improved dramatically, and the hints strengthened. When combined with other measurements, including the cosmic microwave background radiation left over from the Big Bang, distance measurements from supernovae, and observations of how light from distant galaxies is bent by the gravitational influence of dark matter, a pattern emerged. The data increasingly favor models where dark energy evolves over time, where its influence is weakening. The preference for evolving dark energy has not yet reached 5 sigma. but it is growing, and multiple independent lines of evidence are pointing in the same direction. Alexei Lothard-Harnett, co-spokesperson for DESI and a professor at UC Santa Cruz, said it is exciting to think that we may be on the cusp of a major discovery about dark energy and the fundamental nature of our universe. André Couture, a postdoctoral researcher at Lawrence Berkeley National Laboratory, put it another way. He said, "We are in the business of letting the universe tell us how it works, and maybe the universe is telling us it is more complicated than we thought it was." Professor Carlos Frenk from Durham University put it most dramatically. He said that if DESI's hints are right, our earlier understanding goes out the window, and essentially we have to start from scratch. Revising our understanding of basic physics, our understanding of the Big Bang itself, and our understanding of the long-range forecast for the universe. Let me spell out what this could mean for the fate of everything. If dark energy is constant, if the cosmological constant model is correct, then the universe's future is sealed. The expansion will continue accelerating forever. Galaxies will move apart faster and faster. Eventually, the Milky Way and its nearest neighbors will merge into a single supergalaxy. But everything beyond our local group will recede past the cosmic horizon. We will be alone in an observable universe that contains only one galaxy. Stars will burn out. No new stars will form because all the gas will have been exhausted or flung too far apart to collapse. The last red dwarfs, the smallest and most long-lived stars, will finally flicker out in about 100 trillion years. Then the universe will contain only stellar remnants. White dwarfs, neutron stars, black holes. These too will decay. Protons may disintegrate over unimaginably long timescales. Black holes will evaporate through Hawking radiation, a process that takes something like 10 to the 100th power years for the largest ones. Eventually, there will be nothing left but a cold, dark, empty void. No structure, no complexity, no possibility of life or thought or meaning. This is the heat death of the universe, maximum entropy, the end of everything interesting. That has been the assumed fate of the cosmos for the past 2 decades. But if dark energy is weakening, other possibilities emerge, genuinely different possibilities. Futures that we had ruled out might be back on the table. Perhaps dark energy will fade away entirely. The acceleration will stop. The universe's expansion will slow and eventually halt. And then, perhaps, gravity will reassert itself. The expansion will reverse. The universe will begin to contract. Everything that has spent billions of years flying apart will come rushing back together. The cosmic background radiation will blue shift, growing hotter and hotter. Galaxies will merge. Stars will collide. Eventually, all matter and energy will compress back into a singularity. A big crunch. The opposite of the Big Bang. Some physicists have speculated that a big crunch could trigger a new Big Bang, starting the cycle over, an eternal oscillation between expansion and contraction, birth and death and rebirth. This is a more poetic ending than heat death. Not an ending at all, really, but a transformation. Or perhaps dark energy will do something else entirely. Perhaps it will oscillate, strengthening and weakening in cycles we cannot yet predict. Perhaps there are multiple components to dark energy, interacting with each other in ways we have not imagined. The rules that govern it may be far more complex than our simple models suggest. The point is that we do not know. After decades of confidence in the cosmological constant model, the foundations are shaking. And the shaking began with data, with measurements, with rigorous science, not with speculation. Willem Elbers, a postdoctoral researcher at Durham University, captured the mood of the field. He said that for a couple of decades, we have had this standard model of cosmology that is really impressive. As our data are getting more and more precise, we are finding potential cracks in the model and realizing we may need something new to explain all the results together. Mustafa Ishaq Baushaki, a physics professor at the University of Texas at Dallas and co-chair of the DESI working group interpreting cosmological data, has worked on questions of cosmic acceleration for 25 years. He said that if dark energy continues to weaken, eventually it will not be the dominant force in the universe. The expansion will stop accelerating. It could go at a constant rate or even stop and collapse back. Of course, these futures are very remote and will take billions and billions of years to happen. But if the evidence continues to grow, and it is likely to, then this will be huge for cosmology and all of physics. The fate of everything that exists may be up for revision, and the story is still unfolding. Right now, as you read this, photons from distant galaxies are streaming toward DESI's detectors, carrying information about the expansion history of the universe. The answer to how it all ends may be written in that light. So here we are, 5 discoveries, each one profound, each one peer-reviewed, published in the most prestigious journals in science, confirmed by multiple independent teams using different methods and different equipment, each one challenging fundamental assumptions about reality that we have held for decades or centuries. Time has holes. The famous double-slit experiment, the heart of quantum mechanics, now works with slits in time as well as space. The distinction between spatial dimensions and temporal dimensions, which seemed so absolute, so obvious, so built into the structure of experience, is fuzzier than we thought. The heaviest particles communicate instantaneously. Top quarks and anti-top quarks, existing for half a yoctosecond, shorter than any timescale you can meaningfully imagine, remain entangled. Their spins stay correlated, even when no signal traveling at the speed of light could connect them. Einstein's spooky action at a distance extends to the highest energies ever probed. Energy can be teleported from the vacuum. The ground state, the lowest possible energy a quantum system can have, is not as inaccessible as we thought. Through entanglement and classical communication, energy can appear in one place after being injected somewhere else, faster than any physical carrier could transport it. An engine can run on the mathematics of existence. The Pauli exclusion principle, which gives matter its structure and atoms their shells and prevents you from falling through the floor, can be harnessed to do work. Not heat, not fuel. Pure quantum statistics. The force accelerating the universe may be fading. Dark energy, which we thought was a cosmological constant, a fixed feature of empty space, may be evolving. The fate of the cosmos, which we thought was settled, may be up for grabs. Why did you not hear about these? Part of the answer is practical. Science journalism has shrunk. Newspapers that once employed dedicated science writers now rely on wire services and press releases. The complex, nuanced stories get crowded out by the quick and sensational. A story about quantum interference in time requires careful explanation. A story about a celebrity scandal requires none. Part of the answer is that quantum physics is hard. The double-slit experiment in time is difficult to explain even to scientists who do not specialize in optics. The subtleties of top quark entanglement require background in particle physics that most people do not have. We lack the vocabulary to discuss these discoveries casually. They do not fit into tweets or headlines. They resist simplification. Part of the answer is institutional. Academic papers are published in journals that cost thousands of dollars per year to access. Press releases are written for other scientists, not for the public. The machinery that translates research into understanding has broken down. But I think there is a deeper reason. These discoveries are unsettling. They do not just add to our knowledge. They challenge the frameworks we use to understand everything else. And that kind of challenge creates discomfort. It is easier to scroll past. It is easier to let the algorithm show you something that confirms what you already believe. If time can have slits in it, what does that mean for our experience of time? For our sense of before and after? For our belief that the past is fixed and the future is open? We build our lives around the flow of time. We grieve and hope and remember and anticipate. What happens to all of that when time itself becomes manipulable? If the heaviest particles stay entangled despite existing for fractions of a second, what does that say about the nature of connection? About whether anything in the universe is truly separate from anything else? We think of ourselves as individuals, bounded by our skins, isolated in our skulls. What if that isolation is an illusion? What if everything is connected at a level deeper than we can perceive? If we can extract energy from the vacuum, what does that mean for our understanding of nothing? For our sense that empty space is truly empty? The void is not void. The vacuum seethes. The ground state is not the floor. There is always something there, even when there is nothing. If an engine can run on quantum statistics, what does that say about the relationship between mathematics and physics? Is energy just information in a different form? Is the distinction between the abstract and the concrete as meaningful as we thought? The engine runs on the Pauli exclusion principle. It runs on a mathematical rule about what fermions can and cannot do. What does it mean when mathematics can turn a turbine? And if dark energy is changing, if the fate of the universe is genuinely uncertain, how should that affect the way we live? We make plans. We imagine futures. We build things intended to last. All of that rests on assumptions about what kind of universe we live in. If those assumptions are wrong, does anything need to change? I do not have answers to these questions. Neither do the physicists who made these discoveries. What they have are data, measurements, evidence that the universe is stranger than we thought. But the interpretation, the meaning, the implications for how we should live and think and feel, those remain open questions. And perhaps that is okay. Perhaps questions are more valuable than answers, at least some of the time. Perhaps the appropriate response to the weirdness of quantum mechanics, to the vastness of cosmology, to the strangeness of a universe that refuses to fit our intuitions, is not a new dogma, but a new humility. But I believe these stories deserve to be told. Not because understanding quantum physics will change your daily life. Not because you need to know the difference between fermions and bosons to be a good person or a productive citizen. but because knowing the shape of reality, even imperfectly, even through a glass darkly, is part of what it means to be human. We are curious creatures. We ask why. We look up at the stars and wonder what they are. We look down at our hands and wonder what we are. We have been asking these questions since the first humans sat around the first fires, looking up at the night sky, feeling small and confused and awestruck. Science does not give us comfort. It does not tell us that the universe was made for us, that we are special, that things will work out in the end. It tells us that we live on a pale blue dot orbiting an ordinary star in the suburbs of an ordinary galaxy, one among hundreds of billions of galaxies, in a universe that may be one among countless universes. It tells us that we are made of the same stuff as the rocks and the trees and the distant quasars. It tells us that we are brief, that we are small, that we are not the point. But science gives us something else. It gives us truth, or at least our best approximation of truth, our best guess at what is actually happening, tested against reality, refined and revised and improved with each new measurement, each new experiment, each new observation. Science is not a set of facts to be memorized. It is a process, a conversation between humans and the universe, an ongoing negotiation about what is real. And sometimes that conversation reveals something astonishing, something that overturns our assumptions, something that makes us see the world with new eyes. That is what happened in 2023 and 2024. In laboratories and observatories around the world, the universe whispered its secrets and a few people listened. We are the universe trying to understand itself. And in 2023 and 2024 and 2025, we learned that the universe is weirder than we ever imagined. More connected, more dynamic, more uncertain, and in some strange way, more beautiful. These are the headlines that never were, the discoveries that slipped through the cracks, the papers published in Nature and Physical Review that did not make the evening news, the findings that should have sparked dinner table conversations and classroom debates and late-night arguments about the nature of existence. Now you know. Now you can be the one who brings these stories into the world, who tells your friends about the double-slit experiment in time, who explains quantum entanglement at the highest energies, who shares the wonder and the strangeness and the profound unsettlement of learning that reality is not what we thought. The floor beneath you is not as solid as it seems. The atoms that make it up are mostly empty space, held together by quantum forces we barely understand. Time is not as simple as it feels. It can be punctured, manipulated, made to interfere with itself. And the future of everything, of all the stars and all the galaxies and all the dark spaces between them, of every atom that has ever existed or ever will, that future is genuinely uncertain. But there is something beautiful in that uncertainty, something that resembles hope, something that makes the universe feel alive and dynamic rather than dead and determined. Because if we do not know everything, that means there is still more to learn. The greatest discoveries are not behind us. They are not the province of past geniuses, of Newton and Einstein and Feynman, names in textbooks written by people long dead. The greatest discoveries are still waiting. In the quantum vacuum, in the collisions at the LHC, in the light from distant galaxies streaming toward instruments we have only just begun to build. The universe is still speaking. Every photon is a message. Every particle collision is a revelation. Every measurement is a question answered and a dozen new questions raised. The discoveries I have described today the slits in time, the entangled top quarks, the teleported energy, the quantum engine, the weakening dark energy. These are not the end of the story. They are the beginning of a new chapter, a chapter where our instruments are finally precise enough to see what was always there, a chapter where the strangeness of quantum mechanics bleeds into larger and larger scales, a chapter where the fate of the cosmos is back in play. We stand at a remarkable moment in the history of human knowledge. The tools exist to ask questions that were previously unanswerable. The data is coming in faster than we can analyze it. The universe is revealing itself, layer by layer, strange truth by strange truth. The headlines that never were are becoming the foundations of tomorrow's physics. The papers that slipped through the cracks of our attention economy are being cited by the next generation of researchers. The discoveries that seemed too weird, too abstract, too hard to explain are quietly reshaping our understanding of everything. And somewhere, right now, another experiment is running. Another measurement is being made. Another secret is about to be revealed. And if we listen carefully enough, with patience and humility and wonder, we might just hear what the universe has to say